Subscribe our channel, press the bell icon for latest videos.
Hi friends, here in this video we are going to see problem number 3 on deflection of beams that I am going to solve it by using the Macaulay's method. So let's get started. I'll read the question. Here it is given. Determine the deflection at points B, C and D in the beam shown below. The diagram is given to us. The beam has circular cross section of 200 mm diameter. So the diameter of the beam is 200 mm, and from this diameter I calculate the moment of inertia for this circular cross section of beam, which is pi by 64 diameter raised to 4, and I value comes out to be, here I'll keep the diameter in terms of meter, so that would become 0.2 meter. In other words, 200 divided by 1000, and it gives me the answer as 7.85 into 10 raised to minus 5 meter raised to 4. Now after getting this I value, E is also given to us, that is 200 GPa. So I'll convert this as well, and for that I'll say EI will be 200. Now gigapascal is 10 raised to 9 Newton per meter square. Dividing this by 10 raised to 3 will give me the answer in terms of kilopascal, that is kilonewton per meter square. So finally EI value, here this E value, in actual this is E value, I would be multiplied later. So only E value, it is 200 into 10 raised to 6 kilonewton per meter square. Next I'll multiply with I, and I is 7.85 10 raised to minus 5. So finally EI value is 15.71 into 10 raised to 3, and the unit is kilonewton meter square. Now this value of EI would be used in the further part of the problem, which I had calculated first. Now since the beam is given here, it is a simply supported beam, the first step would be to get the values of reactions, that is reaction at A and reaction at B. Calculation of support reactions, for that first summation of Fy is equal to 0, where upward forces are positive and downward forces negative. So therefore Ra and Rb both are upward. Minus 20, minus 30 both are downward. Minus this UDL 10 into 2, its intensity would be 10 multiplied by 2, that would give the point load for the UDL is equal to 0. So Ra plus Rb value is it is 70 kilonewton, and this I'll keep it as equation first. Then I'll take the moments of all forces about point A, and that will give me Rb value first. clockwise moments are positive and anti-clockwise moments negative. So therefore RB comes out to be in anti-clockwise direction, that is minus RB into total distance, which is 5 meters. So it is minus RB into 5. Then this 20 into 1 in clockwise direction, similarly 30 into 4 also in clockwise direction, so plus 20 into 1 plus 30 into 4. Then the UDL portion, UDL is there over a length of 2 meter, so 10 into 2 would give me the point load equivalent of UDL acting at half of 2, that is 1, and from point A the distance would be 1 plus 1, that is 2. So it would be written in this way, that it is plus because clockwise moment. So 10 into 2 and the distance is 1 plus half of 2 is equal to 0, and from this I'll get the answer of RB reaction at B, which comes out to be 36 kilonewton. Now when I get this value, I'll put it in equation 1. So therefore put RB in equation 1. So RA value would be 70 minus 36 and the answer comes out to be 34 kilonewton. Once the reactions are known, I'll indicate them onto the beam. Now this completes the step number 1. For step number 2, I would be using the Macaulay's method, also called as the double integration method. So that is my step number 2. Where I am using the Macaulay's method, and the governing differential equation for the Macaulay's method is EI d square y by dx square, that is equal to moment, and this moment would be taken at section XX. Now, how to take the section XX? From point A, that is from the left part, I am taking a section which is very far away from point A, and the distance from point A is x meters. Now, one very important hint or conclusion here: whenever you have UDL over the beam and you are using the Macaulay's method, in that see to it that if the UDL is anywhere in between the beam or at the end, if it is not there at the end, like if we see into this given problem, the UDL is there only in this C to D portion, it is not there in AC portion or BE portion. So if it is not extended up to the end, in that case bring that UDL up to the section, like section X. So here I would be extending this UDL from point D up to section X. Extend this. After extending it over here, it would be having the same intensity, which is 10 kilonewton per meter. And like I have extended the UDL in the top portion from D to B or up to section X, similarly at the bottom portion also I'll have to show the value of UDL, which is acting from the bottom, and this UDL would also have the same intensity. like 10 kilonewton per meter. This step needs to be followed if the UDL is there anywhere in between the beam. You'll have to extend it over to the section X or up to the end. Now, if this UDL would have been in this AC portion, no need of this step. Similarly, if it would have been in this BE portion or in contact with any of the ends, then this step is not required. The step shown here is to be used when the UDL is there anywhere in between the beam. Now, after taking the section, the next step would be to take the moments about this section. Starting with RA, RA is producing a clockwise moment at section X, so that is to be treated as plus as per the sign convention. Clockwise moments would be taken positive and anti-clockwise moments negative. So therefore, EI d square y by dx square will remain as it is. Taking moment RA into X. Next, this 20 kilonewton load is producing a moment in anti-clockwise direction for section X. So it would be minus, and the distance between the section X and this force is X minus 1 meter. So it would be written like this: minus 20 into X minus 1. Then there is another point load of 30 kilonewton. It would also be producing an anti-clockwise moment, and the distance between the section X and this force is X minus 3 meters, or X minus, it is 4 meter exactly, because the point load is at 4 meter distance from A. So X minus 4 is the distance, and anti-clockwise, so minus 30 into X minus 4. Then after the point loads, then there are UDL. When I see here, there is an upward here, the UDL which is shown previously into the problem, having 10 kilonewton per meter extended up to point B. So that is the UDL, and the distance it covers is X minus 1. That is the distance of this UDL which is in the downward direction, and it would be producing an anti-clockwise moment. So minus, here I will explain it in this way by writing minus 10 into the distance is X minus 1. That is the value of point load equivalent to this UDL at X minus 1, and it would be acting at half of X minus 1 when I take the moment. So half of X minus 1. Then at last there is even UDL in this upward direction of same intensity, and this UDL will be producing moment in the clockwise direction, so that will be plus. It is acting at a distance of X minus 3 meters, so that would be plus 10 into X minus 3 and acting at X minus 3 half. So this is the entire equation. Here I will be putting the value of RA. This would be 10 by 2, and X minus 1, the bracket into X minus 1, that would be X minus 1 whole square by 2 plus 10 by 2. This will be X minus 3 whole square. Now, after reaching up till this equation, I would be integrating this once to get the slope equation. So Integrating this equation once, we get EI would remain as it is, d square y by dx square will become dy by dx. Next, it is 34x, so that will become 34x square by 2. And since I am integrating it for the first time, there will be a constant c1 added. Next, minus 20 into x minus 1 will become x minus 1 whole square by 2. Next, minus 30 x minus 4 will become x minus 4 whole square by 2. Then minus 10 by 2 is as it is, and x minus 1 whole square will become x minus 1 whole cube by 3. Then plus 10 by 2 will remain as it is, and x minus 3 whole square will become x minus 3 whole cube by 3. So on simplification, this would give me 2 into 3 would be 6. So this is the slope equation. I'll be keeping this equation as equation second, and it is giving me the slope equation. Next, integrating this equation again will give me the deflection equation. So integrating again, and that is why it is called as the Macaulay's method, where we use the double integration. EI will remain as it is. Dy by dx will become y, plus it is equal to 34 by 2 will remain as it is, and this will become x square will become x cube by 3, plus c1 will be c1 into x, plus another constant c2 because I am integrating it for the second time, minus 20 by 2. Then x minus 1 whole square will become x minus 1 whole cube by 3, 30 by 2, x minus 4 whole square will become again whole cube by 3, 10 by 6, x minus 1 whole cube would be x minus 1 raised to power 4 by 4, 10 by 6, x minus 3 raised to power 3 would be x minus 3 raised to power 4 by 4. So simplifying this equation, (34 x cube by 6 plus c1x plus c2 minus 20 x minus 1 whole cube. This is 6. Six into 4, that is 24, and even on to the other side also it is the same value. So here is equation 3 and it gives me the deflection equation. Now after getting the deflection equation, I need to calculate the constants C1 and C2. For that I would be using the boundary conditions, that is using the following boundary conditions, that is at x is equal to 0 from where we are measuring the distance, the deflection y is 0. This is the first boundary condition. Next, at x is equal to the total distance of the total span of the beam, which is 3 plus 2, that is 5 meter. So at x is equal to 5, y is equal to 0. Again, since it is supported, so putting these boundary conditions one by one in the deflection equation. Here also I am mentioning an important hint here. That to calculate C1 and C2, put boundary conditions in the deflection equation. That is, don't put the boundary conditions into the slope equation, put it in the deflection equation. So I'll put the first boundary condition over here. So therefore, at x is equal to 0, y is 0, so left hand side will become 0. Then x is 0, first term also goes, that is, it is 0. Next, plus c1 into x, x is 0, so it also becomes 0, plus c2. Now when I put 0 here, this bracket is going to give me 0 minus 1 negative answer. Similarly, all the brackets continuously are giving me negative answers when I put x is equal to 0. So don't consider these brackets, they don't have to be considered into the solution until they give the positive answer. So c2 value will be 0. Then putting the second boundary condition, that is at x is equal to 5 meter, y is 0, so left hand side would be 0. And here I have 34 upon 6. Instead of x, I'll put 5, so it will be 5 cube. 5 cube plus c1 into x, x is 5, so it will be 5 c1. Plus c2 value is 0, then minus, again putting into the brackets, just check for the positive answer. It is 5 minus 1, this bracket needs to be considered, so it is minus 20 into 5 minus 1 whole cube by 6, then minus the next bracket. Again, when I see all the brackets here, they are going to give me positive answer when I take x is equal to 5, so all of them are to be considered. I am writing the brackets throughout, so the values would be in this order. So on calculating this, after the solving of this, I'll get the answer of C1, which comes out to be, it is minus 78. After getting the value of C1, I'll put it in equation 2 to get the slope equation. So therefore, put C1 is equal to minus 78 in equation second. So therefore, in equation second, we have the slope equation. Here C1 would be replaced, its value would be minus 78 and the rest remains same. So this is the slope equation, wherein I'll call it as equation A. The final slope equation. It means whatever at whichever distance in the beam we have to find the slope, we can find it by using this equation. Just by putting the distance, that is x, we can get the value of respective slopes. Now in a similar manner, I'll put C1 and C2 in equation 3 to get the deflection equation, which would be the final deflection equation. So therefore, put C1 minus 78 and C2 is equal to 0 in equation 3. So therefore, it would be EI into Y. Putting C1, C2 values, remaining all terms would be as it is. C2 value is 0, so directly neglected. Then putting all the terms as it is. Here is the equation, which is the final deflection equation, and whatever is asked in the problem, for that I will be using this equation. Equation B, that is final deflection equation. Now I look into the question what has been asked for us. The question is, they had said that determine the deflection at points B, C and D. It means we have to find deflection at point B, at point C and at point D. So starting with the first point, that is point B, as mentioned in this boundary condition, here the deflection is already 0 because it is supported. So first question has been answered. y suffix b would be equal to 0. Why? Because it is supported. So this is y suffix b. First answer. Next, we have to calculate the deflection at y is equal to c, which is at 1 meter distance. So x would be 1 meter. So here I mention that it is calculation of deflection at point C, that is y suffix c. For that, x value is 1 meter. So putting it into equation B, that is the deflection equation, and therefore it would be EI, y would be y suffix c, which we have to calculate, 34 1 cube by 6, because I have to put the value as 1, and remember checking the brackets. Here first I'll write down minus 78 into 1. Next, check the brackets. If they are giving you the answer as 0 or negative, neglect those brackets. Consider only the positive value into the brackets. So when I put the value as 1, this becomes 0. In the further part, that also gives me 0 or negative answers. So neglecting all these terms, we will just write the equation up to minus 78 into x. That would be the deflection. And finally, this answer comes out to be minus 72.33 divided by EI, and EI term is already there with us in the data. This I had calculated initially, that came out to be 15.71 into 10 raised to 3 kilonewton meter square. And why we are putting it in terms of kilonewton meter square? The reason simple being that loads are given in terms of kilonewton and distances are in the form of meter. So even EI value should be in the form of kilonewton and meter. So after the calculation, YC value comes out to be minus 4.60 into 10 raised to minus 3 meter, or it is minus 4.60 mm. That's the second answer. Negative sign indicates that deflection is in downward direction. That is the meaning of this negative sign over here. At last, we have to calculate the deflection at point D. For that, the distance would be, it is at 4 meter from A, so x is equal to 4 meter. D is at x is equal to 3 meter. It is not at 4, at 4 it is E. So I have to take x is equal to 3 meter. So therefore, putting the value in this final deflection equation, so it is calculation of deflection at point D. For that, I have to put x is equal to 3 meter in the final deflection equation, that is in equation B. So in equation B, I will be putting the values over here. EI left hand side would be as it is, y suffix d, the deflection. It is 34 by 6. Instead of x, it would be 3. Now again, when we are seeing the brackets, see to it that only those brackets are taken whose values are positive. 0 and negative are not allowed here. So it would be x minus 3, that is x minus 1, that is 3 minus 1 whole cube by 6. Next, after that, this bracket won't be considered because when I put x is equal to 3, 3 minus 4, this is negative, it won't be considered. Here this bracket would be taken. So minus 10 into 3 minus 1 raised to power 4 divided by 24. And at last, when I put x equal to 3 here, even this gives me 0 answer. So won't be considered. We'll write the equation only up till here. And therefore, EI into y suffix d, that is equal to minus 114.34. Therefore, y suffix d would be divided by EI, whose value is 15.71 into 10 raised to 3 kilonewton meter square. And the answer of y suffix d is minus 7.28 into 10 raised to minus 3 meter, or minus 7.28 mm. That's the third answer. And here also, negative sign indicates downward deflection. So these are the final answers. That is, we had calculated the value of y suffix b, the deflection at point B, at point C and point D. And with this, the problem gets completed. And if you all find my videos helpful, you all can like, comment, share and subscribe these videos and share amongst your family and friends. Thanks a lot.